I want to create even more connections between our understandings of singularities, black holes, and ourselves. All of these ideas have been put together based on lots of research. I'm learning along with you. Your comments inspire me to learn and grow more so that we may grow together and change the world for the better. Now, I'm about ready to make these videos on a weekly basis again, but I can't make them alone. It's a huge, colossal task. So, in order to do this, I'm gonna need some help. Let's see, maybe I can create some assistance. Let's start with a little, perhaps someone with a bit more female energy. She's gotta be an incredible artist. And lots of fun to hang out with. Well, hi there. Can you help me talk about some stuff? Awesome, here we go. I want to talk about singularities. Why is it that we generally only think about singularities as they relate to huge things, like black holes and galaxies? From that perspective, it's so far out there that we have no way of identifying it with it personally. How does a black hole relate to me? What can we do with all the information available about them? Do we see singularities anywhere else in our reality? Perhaps it's something that we can relate to on a personal level. And for that matter, what is a singularity, really? Well, the modern definition of a singularity is the state, quality, or condition of being singular. It's also known as the point at which a function takes an infinite value. Interesting. 0 and 1, all at the same time. Singularities were first coined as a description of the singular space from which all things came from before the creation of the universe through the Big Bang. This idea was then carried over to describe what happens inside a black hole. And then they were related to singular points in general across our various scientific fields in mathematics, both observational as well as theoretical. This is exciting. Singularities are not solely limited to black holes. They appear everywhere. We just have to practice identifying them. One of the best examples we have at our disposal is a waveform. A sine wave continually oscillates back and forth between a center point, a singular point between the yin and yang. This is a singularity in motion. I mean, you know as well as I do that, especially since radio technology, the use and recognition of waveforms is present all over the place. It's even what we see when we look at the spectrum of light through a digital lens. So we have all kinds of singularities that we know of today, and oftentimes they're represented by a dot. In modern mathematics and geometrics, we have mathematical singularities, singular points on curves, rational singularities, isolated singularities, movable and removable singularities. These are all describing more complex versions of that sine wave singularity that I first showed you. We also have the idea of technological singularities, but we're gonna save that one in our pocket for another episode soon. Now, one thing we cannot see is the black hole itself, given that they absorb light. Because of that, one of the ways that we have identified black holes is by looking at the results. Celestial bodies orbiting around a singular space at a very high speed, dictating that something must be having an effect on them, which has a very powerful gravity. Just like with a waveform, they both oscillate up and down between a center point. And I'll agree with you that it's a very small and subtle similarity. At face value, a waveform and a bunch of stuff flying around a sphere in space seem completely different. At the same time, just ask yourself, if you were to map out what this three-dimensional perspective looked like in 2 dimensions, what would it look like? Maybe something like this? And what if you mapped that out over time? Interesting. In this way, the very large harmonize with the very small, and we are exactly in the middle of that. And that's really the whole point. Einstein, one of the most beloved characters in the storybook of mankind, took up a quest for truth, which set him about on an expedition to find a theory of everything. Upon opening the door to general relativity to the world, he then journeyed to find a way to unite the forces of relativity and the world of the quantum. A theory where the very big and the very small come together as one. And ever since then, that's what's been up. Scientists everywhere have been striving to do this. But the problem was that general relativity and quantum mechanics appear to be two completely different things from each other, completely contradictory in every way. And that's another trick. We just don't know how they come together, but we do know that they do. They have to. What we know scientifically about black holes is that they demonstrate the laws of both the quantum world and general relativity simultaneously, and it is baffling to us. In order to fit these two theories together, we have to know the structure of the vacuum. By knowing the structure, the geometry of the vacuum of space, we could superimpose it on both of our scientific models, the quantum and the relative. We would certainly see where these models would break, but we would also see where they come together. We would develop new models based on our new understandings and use it to create the most amazing world to live in. I mean, that might even be the secret to a universal flow of free energy, or even flying cars. So yeah, let's talk about that. We'll see you next Monday.